Hi there. We're going to go ahead and take a look at the 10B Connect homework. I'm going to go ahead and share the screen with you here so you can see the homework, and then I'll move to another so that we can actually kind of draw out some of what we're looking at. So let me go ahead and get this off of the page. But basically 10B is going to be using our normal distribution curve to help us answer questions about what percentage of parts are we going to be able to deliver to our customer given what we know about our process. Okay, so if we just read the problem, it says part of the process for improving the quality of their cars, engineers have identified a potential improvement to the process that makes a washer that is used in the accelerator assembly. The tolerances on the thickness of the washer are fairly large since the fit can be loose. But if it does happen to get too large, it can cause the accelerator to bind and create a potential problem for the driver. Note this part of the case has been fabricated for teaching purposes. So let's assume that as a first step to improving the process, a sample of 40 washers comes from the machine that produces the washers, was taken and the thickness measured in millimeters. So the data below is the measurements from our sample. So we want to use Excel to help us answer the question. If the specification is such that no washer should be greater than 2.4 millimeters, assuming that the thicknesses are distributed normally, what percentage of output is expected to be greater than this thickness? Okay, so the answer to that question is a multi-step solution. Okay, and so the first thing that we need to do is we need to take this data and we need to put it into Excel. And I'm just going to open up a blank sheet in Excel, and we'll bring that over here and I'll copy that data in. And so in order to put this data on the normal distribution curve, right, we need to know both the mean. So I'm going to put the average of the data, and we're going to figure that by using this function over here. We're going to go average, and we're just going to highlight all of this data. Boom. Okay, so our average is 1.9625. We also need to know the standard deviation. So to find the standard deviation, what I'm going to do is I'm going to use function, and I'm going to type in up here. If I want to know the standard deviation, what function should I use? It returns STDEV. So estimate standard deviation based on a sample. Okay, so what we're going to do is we're going to use that function. And again, we're going to highlight that same set of data. Boom, boom. And so now we know that our data has an average of 1.9625 and a standard deviation of 0.20962. Okay, so let's use that then and think about what that means to our normal distribution curve. All right, so I'm going to stop sharing this screen and go to one that I can draw on. And we're going to draw that onto this screen. Okay, so let me make that a full screen for us. Okay, so now I've got my full screen. And so I'm going to draw on here using, I'm going to use purple to represent the process, right? And so what we know is that the mean of our process is 1.9625, okay? And that one standard deviation is 0.20962. So a lot of times if we think about the mean and the standard deviations, if I come almost all the way out to the end, right, I know that there are basically this isn't going to be proportionate, but you'll get the idea. Yeah, sorry, that was not proportionate. Let me try that again. It's not really wanting me to draw here. I don't know why. Here, first off, I'm going to erase these. Boom, boom. And then we'll come back over here. And we'll use the pen. And we'll, again, be using purple. And so 3 standard deviations is going to be about right here, right? Which would make then 1 standard deviation about here, and 2 standard deviations about here. And we do that on the reverse side of it, -1 standard deviation, -2 standard deviations, and -3 standard deviations. And you're going to pretend like those are equidistant apart, right? So if I know that my mean is 1.9625 and that my standard deviation is 0.20962, right? I can then make the conclusion that one standard deviation away from the mean is 1.9625 plus 0.20962, which equals 2.172. And 2 standard deviations away from the mean, I'm going to add another 2.0962, and that's equal to 2.382. Oops, 382. And 3 standard deviations, 0.20962. Oops, that didn't work right. 2.382 plus 0.20962 is equal to 0.2592. So this is going to be, roughly where we're at, 2.592. And then -1 standard deviation, -2 standard deviations, and -3 standard deviations. We're just going to take the 1.9625 and subtract 0.20962, right? So that makes this then 1.753 minus 0.20962, 1.543, and minus 0.20962 is 1.334. 1.334. Okay, so because we've converted this into our normal distribution curve, and we've identified 1 standard deviation above the mean, 2 standard deviations above the mean, and 3 standard deviations above the mean, these are our z-scores, right? Perfectly identified at 1, 2, and 3, okay? So, and what we know about z-scores is that in between +3 standard deviations and -3 standard deviations, we have, so between +3 and -3 standard deviations, we have about 99.97% of our values, okay? And the reason that we use those z-scores is if I have the actual value, I can't convert that to percentages of values under the table. But when I convert my actual values into z-scores, right, I can look up either in Excel or using a table and find out based on a particular z-score, what percentage of the values are going to be above or below the mean, okay? So if we return to our problem, let me find the problem and pop it back up on the screen for us. Boom. So the problem says, all right, if the specification is such that no washer should be greater than 2.4 millimeters, assuming that the thicknesses are distributed normally, what percentage of output is expected to be greater than this thickness? Okay, so basically we've drawn on here what the process is capable of. Now we're going to say, all right, our customer would like to know, or these engineers would like to know, and we're just going to roughly estimate the value of 2.4. And what they would like to know is what percentage of values or how many washers are we not going to be able to meet? Well, anything under this, we're going to be able to meet. Anything greater than this mark, right, we're not going to be able to achieve. So what we do is we have to find the z-score of 2.4, right? So a z-score, we calculate a z-score by taking our raw score minus the mean and dividing it by the standard deviation. And that will tell us how many standard deviations away from the mean our 2.4 is. So we're going to take 2.4, whoops. We're going to take 2.4 minus our mean of 1.9625 and divide it by our standard deviation of 0.20962. 2.962. Okay, so I'm going to do that on my calculator. I'm going to go 2.4 minus 1.9625. And I have that equal to 0.4375 and divided by 0.20962. That's going to return a z-score of 2.087 is equal to 2.087. That's my z-score. Okay. So what my z-score does is it allows me then in Excel to use a function in Excel. I don't know why I'm stuck here. I'm going to pause recording while I figure out why I'm stuck. Don't know why I was stuck, but I got it fixed, right? So we had calculated our z-score, right? So our z-score was 2.087, all right? So I can use the function norms distribute. So I'm going to come here and I'm going to type in NORMS-DIST. And here it is. I'm going to say, okay. And I'm going to have it use the z-score that we did of 2.087. And it's going to return a value of 98.156%. Okay. So if I change that to percent and give it a couple of decimal places, right? That gives me, we'll give it 98.156%, right? So what that tells me is that this space from here, oops, lost it. Let me bring it back. Let me get my pen back here. So I'm going to use the pen and we're going to use orange. And so this space here, sorry, that's not really a straight line, but you get the idea. 98.156% of my values are going to fall on the left side of where my z-score is, right? And so, or the value of 2.4 is. But what I'm interested in answering this problem is actually this portion. So to get to that portion, it's 100% of the values lie underneath the normal distribution curve. So I have to subtract the 98.156 from 100% to get to my z, to get to that percentage, right? So it's going to be is equal to this, excuse me, is equal to 1 or 100% minus 98.156. Boom. Says 1.844% of my values are going to be to the right of that score. So I'm not, that means that 1.844% of the time, my output is going to be greater than 2.4 millimeters. All right. So let's go back to the problem and see what do we need to do. We want to keep that. And so what do we need to do if we want to answer the questions, right? So here's our question. Well, it just asks us the percentage of output. We've got that. It's 1.84%, right? So what if there is an upper and lower specification where the upper thickness limit is 2.4 and the lower thickness limit is 1.4? What percentage of output is expected to be out of tolerance? Okay, so then what we're going to do is we're going to come back to our drawing. And we're going to say, we're going to show on our drawing, and I do this just so you can visualize what we're talking about. So our top side was 2.4 and our bottom side is 1.4. So I'm going to add that in orange. And I'm going to say 1.4 is going to be somewhere in here, right? This is going to be our actual value is 1.4. Well, I need to convert that 1.4 to a z-score. So I'm going to say then my z-score is still the raw score minus the mean. So the raw score here is, boom, 1.4 minus the mean of 1.9625. divided by the standard deviation of 0.20962. And so my z-score, right, is going to equal, getting my calculator out here, and you can do this in Excel, but I wanted you to be able to see it on the actual normal distribution. So I'm going to take 1.4 minus 1.9625 and divide that by the standard deviation of 0.20962, right? And that gives me a z-score of negative 2.683, right? And that should make sense to us that it's negative because we're on the underneath side of the mean, right? So my z-score here is minus 2.683. So I'm going to use that z-score and norms distribution again to find the value of basically, whoops, again, sometimes when I go away and come back, it's not very happy with me. So we'll come back here and go, let's make sure we're using the pen, we're using orange, and we're going to try and find the percentage of values that fall to the left of 1.4, because that would be outside of our lower specification limit. All right. So coming back to Excel, right, we say that our z-score is negative 0.2683 minus 2.683, right? And I can find the value of that by taking that norms distribution again, norms distribution, open parentheses, negative 2.683, boom, close parentheses. Oh, I know why. It's because I didn't have this is minus 2.683, right? And let's go ahead and leave that at 3 decimal places. And we're going to go, again, norms, dist, open parenthesis, our z-score, right? And it tells us that that's 0.0368365. And basically we want that to be a percentage, right? And we're going to take that to 3 decimal places, right? But the question asks us in total. So we have to, when we do the in total, we have to look at both this side, right, and the lower side. So we need to add these 2 percentages together to be able to answer our question, okay? So let's come back to our Excel file, and we're going to add those 2 together, and we're going to say, well, that's going to be equal to 1.844 plus the lower tail, the 0.365 percentage. So our answer is going to be the 2.209, right? So let's compare that to where we're at with our practice problem. So 2.209 rounds to 2.221. So we're on target. All right. Then it says